Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. In the last class we have started drying technology. Drying is a very important unit operation for food processing, and we have started the basic understanding of drying mechanism, the different objective of drying, and then we have moved on to the psychrometry, which is the important study related to the moist air properties, and it is very important for identifying the air conditions when we expose any food material to the convective drying or any processing where the any drying experiment where we use the dry air to remove the moisture from the food product. So, today we will continue with the different psychrometric properties and different operations, different conditions when drying, heating, humidification, all these phenomena happen. Then what is the condition of the drying air, and also we will see the further further drying mechanism and the different rate of the drying process, for example, the constant and falling rate. Okay. So, let us start from the psychrometry. Psychrometric properties, we have discussed wet bulb temperature, dry bulb temperature, then humidity ratio, specific humidity, humid volume, and then enthalpy, all these properties. So, today we will see that wet bulb temperature in a bit detail. Wet bulb temperature is the temperature measured by thermometer whose bulb is covered with wet cloth. That means, when we normally measure the temperature in a dry bulb situation where we do not cover the bulb of the thermometer with a wet cloth, that time the normal temperature of the air that we can measure is called the dry bulb temperature. Now, when we covered with a wet wick the bulb of the thermometer, then what happen is that it will try to come to an equilibrium situation, because all the moisture will evaporate when it comes in contact with the dry air. So, the air starts to get saturated. However, since the moisture takes the latent heat of vaporization from the thermometer liquid itself, so the temperature is reducing, and that can be shown here by a lowering in the temperature. So, this is called the difference of this dry bulb and wet bulb is called the wet bulb depression, and thereby the wet bulb temperature is always lower than the dry bulb temperature. Okay. So, if we consider that the heat required to evaporate this is coming from the air. Okay. So, it will give the temperature of that air slightly lower. So, that can be considered as H into T minus Ta. H is the convective heat transfer coefficient and T minus Tw, T is the temperature of the dry bulb and Tw is the temperature of the wet bulb condition. So, T minus Tw into H, that will be equated with the amount of moisture which is evaporated into the latent heat lambda W. Okay. So, if H, capital H and Hw, these are the humidity of the air and the saturated air. Okay. So, and Mb is the molecular weight of air, Ky is the mass transfer coefficient. So, we can write that lambda W divided by Mb Ky, okay, into H minus Hw, that is equal to small h into T minus Tw. Okay, so this is the relation, and H by MBKY, this is called the psychrometric ratio. Now, if we look into the psychrometric chart, okay, so the horizontal line at the bottom, this boundary, the lower boundary, this is showing the dry bulb temperature, and this ordinate is showing the humidity ratio, that is kg of moisture H2O per kg dry air. This yellow line is showing the constant enthalpy line, and this orange line is constant wet bulb line. So, for example, if we consider that if let us say we take a dry bulb temperature here, and then for this dry bulb temperature, if we cover the bulb of the thermometer with a wet cloth, okay, and then we try to make it equilibrate, then it follows this wet bulb line and reaches this 100% saturation. Okay. So, if we measure the wet bulb temperature, that will be here. So, this will be TW, where this will be T. Okay. Now, there is a difference, there is a slight difference between a line of constant wet bulb and line of the constant enthalpy. However, in many cases we consider them equal, but there is a little difference. This is because the constant wet bulb line, we can get this situation by many combination of humidity and dry bulb temperature. Okay. So, we can take any humidity ratio value and any temperature that will follow this constant wet bulb line. Okay. Now, however, when we talk about enthalpy, that is enthalpy of the dry air plus the enthalpy of the water vapor. Okay. So, it has been seen that there little difference we can observe between these two values. Therefore, when we consider the difference of enthalpy from a fixed point, so better to consider that enthalpy directly from that point and the other point when we finally reaches. So, the difference between these two will give us the enthalpy difference of those 2 points, but that does not follow the exact line of the wet bulb temperature. Okay. So, next is, if we consider that what are the parameters that we can understand or that we can read from the psychrometric chart. Psychrometric chart, although available for different pressure and temperature condition, but mostly that we use for the drying air analysis, that is ranging from 0 to 50 degree Celsius at atmospheric pressure. Although ASHRAE have developed different different psychrometric chart for different conditions, for example, -40 to 10 degree Celsius or even very high temperature as well. But for our need, we will consider this one, and if the chart has been drawn at atmospheric pressure and we know any 2 property of this moist air, so the all other property we can calculate. For example, if we know the dry bulb temperature and any other condition, for example, the relative humidity, okay, then all other condition we can calculate. So, here we can see that the slanting line, the green slanting line, these are the wet bulb line. The white line, these are called the specific volume line, okay, specific volume, and the line which is making this curved line towards the left end, that is saturation curve or the relative humidity showing first one is 100% saturation, and then as we move towards the right side, the relative humidity is reducing. Okay. The vertical straight line, these are the dry bulb temperature line. Saturation curve is the 100% relative humidity curve. Okay. So, we will see that how from two data of the any property of the psychrometric chart we can calculate the all other properties. For example, here in this psychrometric chart we have taken a condition, that is dry bulb temperature is 32 degree Celsius and relative humidity is 60%. Determine the remaining psychrometric properties. So, in the dry bulb temperature line, that is this ordinate, we can first see the 32 degree temperature. So, this is here 32 degree temperature, and then when it reaches to 60% RH. So, we will draw a vertical line, okay, we draw a vertical line, and then we come to this point, that is 60% relative humidity, and then we horizontally move to the right to find out what is the specific humidity. Okay. And at this point we will get the specific humidity. Here the unit has been given as gram moisture per kilogram. Okay. So, here we are getting 18, we can convert it to kg moisture per kg dry air as well, and then from this point we can calculate that what is the value of the humid volume. So, we follow the slanting line, we can see that this is coming around V equal to 0.89 meter cube per kg. So, humid volume that we can get from this line. Also we can get the enthalpy if we draw a line straight away through the constant enthalpy line. So, we can find that enthalpy is coming 78 kilojoule per kg air. So, this is how we can calculate all the parameters of the psychrometric chart. Now, then what we can calculate is wet bulb temperature and dew point temperature. So, what is wet bulb temperature? Now, we have to follow the constant wet bulb line, okay, which is many a case is just to be taken as similar to the enthalpy line, and then we need to reach the 100% saturation. Okay. So, here we will follow that, and when we reach the 100% saturation and then we draw a vertical line. So, this vertical line is coming 25 degree. Okay. If you follow that from this point, which is the junction point of the 60% relative humidity and 32 degree dry bulb temperature, we will move along the constant wet bulb line, and when we reach the 100% saturation we draw the vertical line, okay, and then we can find out what is the wet bulb temperature. And if we go by constant wet bulb line, we can see that the humidity is also increasing. Right, humidity is also increasing. So, what is dew point temperature? That if we do not increase the humidity of that air, but that air becomes saturated with the moisture present in it, then what we can do? We should lower the temperature of it, okay, with the constant specific humidity, and then when it reaches the 100% saturation, then we can draw a vertical line to find what is the temperature. So, this temperature is coming 23 degree Celsius. So, DPT, dew point temperature, is 23 degree, wet bulb is 25 degree, enthalpy is 78 kilojoule per kg dry air, and specific volume is 0.89 meter cube per kg. So, this is how we can calculate the different properties of the psychrometric chart. Now, there are different processes that we can very clearly show in the psychometric chart, okay, because many a time we need only the sensible heating or cooling mechanism, okay, and in many process what we can do is cooling and humidification, that is the temperature of the air is reducing, at the same time moisture content is increasing, or cooling and dehumidification, that is moisture is also getting lowered with lowering of temperature. Then heating and humidification, heating and dehumidification, and mixing of air streams. Okay. So, if we look into this psychrometric chart, so if we follow the sensible heating, it will go through this line, and sensible cooling will be lowering of the dry bulb temperature. So, it will follow this line. If we say that heating and humidification, so heating, if we move towards the right direction, that is heating, and since here humidification is needed, that means the moisture content, specific humidity should increase. So, this will follow this line. The reverse would be dehumidification with cooling. So, we will follow this line, and humidification and cooling. So, temperature should be reduced, at the same time humidification will be there. So, we will follow this line, and dehumidification with the dehumidifying with desiccant, that will follow this line, and humidifying and dehumidifying without change in temperature. So, this is this vertical line. Okay. Now, we will see this processes. First, let us see sensible cooling. Okay. So, what happened during this process? The humidity of the air remained constant, okay, but its temperature decreases as it flows over the cooling coil. So, when the air needs to flow over the cooling coil, so its okay. So, when the air is passing through the cooling coil, so whatever humidity it has, it will retain that, however, its temperature is reducing. Okay. So, sensibly the temperature is reducing, and since temperature is reducing, their energy of this air will change. So, how much will be the change? So, that we can calculate by this QC, that is equal to MA, that is the mass of air, into HO minus HA. So, HO is the enthalpy of the initial position, and MA, when it reaches to the A, that time the enthalpy will be HA. So, that is equal to, what is enthalpy? Enthalpy is the specific heat into temperature drop. So, CPM into TO minus TA. So, TO and TA we can calculate from this is TO and this is TA. Okay. Then sensible heating. So, sensible heating, during this process the humidity of the air remain constant, but its temperature increases as it flows over a heating coil. Okay. So, here just the reverse thing we can observe, that since when the air gets cool, so its energy reduces, that is why we have done HO minus HA into MA, and when it increases, the temperature of the air is increases, that time the energy will be positive. So, energy will be gained by the air. Okay. So, this is the condition. Now, so change in enthalpy we can get by this equation. So, cooling and humidification. What happened during this process? That the air temperature drops and its humidity increases. Okay. So, cooling and humidification, that means the air temperature will be dropped, but the humidity will increase. So, this happen in case of spraying cool water in the air stream. So, what happened that the air which is entering from the inlet side having the temperature TO, moisture content WO, enthalpy HO, okay, and the mass of the air is Ma. So, this air when flows over the spray of the water, okay, then its temperature and moisture content enthalpy changes, only the mass of the air remain constant. Now, if we see this behavior that at TO, this is the dry bulb temperature TO, at this temperature the inlet air enters. So, at TO temperature it has entered, and then because it has passed through the water spray, so it has to increase its humidity, okay. So, it will follow this line. Okay. So, its humidity increased from WO to WE. So, this was WO initially, now this is WE, and the temperature changed to TE. So, if not fully saturated, after certain increase of the RH may happen. So, corresponding to whatever the moisture has been added to it, we will calculate what is the exit temperature of that, what is the dry bulb temperature now, and then if we want to know the difference in the enthalpy, so we will take the difference of the first point and when it reaches in the second point. So, what is the difference in the enthalpy, that also we can calculate from this. And if we want to find the dPt, that is if this the air is saturated with whatever moisture it has, then it has to follow this direction and should reach the 100% RH line here, and then we find out the dew point temperature. So, in this case the temperature of the exit air should be within the dew point temperature and the inlet temperature. So, it should be higher than the dew point, but lower than the inlet air temperature. So, cooling and dehumidification, just now we have seen that cooling and humidification. Now, when moist air is cool below its dew point, so if it cools below its dew point, then some moisture will condense of the air and leaves the air stream as liquid. As a result, both the temperature and the humidity ratio of the air decreases. So, what happened, we can see in the psychrometric chart that cooling and dehumidification in the initial condition 1, when the dry bulb temperature was dB1, that time when if the air gets cool, okay, it reaches to condition 2. So, first it will come to this condition dP1, but since it reaches 100% saturation, so some moisture will be removed, okay, and some moisture will be condensed. So, then we can calculate that if those moisture will be condensed out, then with the remaining moisture, initial the specific humidity was here. Now, when some amount of condensation has occurred, then the humidity has reduced from here to here. So, the dry bulb temperature of the exit will be this one. And enthalpy, if you want to know, so enthalpy at the first point will follow the constant enthalpy line. So, H1, and in the second position also will follow the constant enthalpy line. So, we will get H2. So, because some moisture has been condensed, so they have released the heat to the ambient. So, we are getting slightly lower in the enthalpy value. Okay. So, this kind of phenomena we can observe in the air conditioning system, although in our case most of the time when we perform the drying operation, so the air has to take the extra moisture of the food. So, most of the time we are interested in the humidification of the air and the drying of the product. But since the psychrometric chart deals with all the required operations, so we are just giving understanding of that how we can calculate. So, then heating and humidification. Okay. So, heating and humidification, if you want to perform, here is a heating coil through which the air when enters, it will first get heated and then again flows over the water spray, and then because of that its temperature and the humidity, specific humidity both increases. So, it follow this line, okay, and we can calculate the difference in the enthalpy. So, this is how we can calculate the mass of the water, that is Ma, which is the mass of the dry air, into moisture content kg H2 per kg dry air. Wo is the final initial condition and Wd is the final condition. So, that will give us the mass of water that has been added to it, and also the change in enthalpy that we can calculate. Heating and dehumidification. So, in this process the air temperature increases and its humidity decreases. So, in this process what happened, that when the air is coming, which is the when the air is coming and it is crossing through a heat exchanger, so it is taking the heat, so temperature is increasing, okay, and then it moves over the desiccant rotor. So, that is taking away the moisture of it, so that we are getting the dry and heated air out of the system. So, it will follow from this point, if you consider, okay, from this point to heating and dehumidification, point 2. So, we are getting the dry bulb temperature here, we are getting a lowering of the humidity, and also we can assess the difference in the enthalpy between these 2 points. Then mixing of air streams. So, mixing of air streams also important in certain cases of the drying operation, where we want to recirculate some amount of the exit air with the inlet air, because in some hot air drying this kind of phenomena is being done to make the product quality better, because if we use excess amount of hot and dehumidified air, and sometime case hardening and all this phenomena may happen. So, that is why this kind of recirculation or mixing of the air stream may be done. So, what happened in this case, that during this process 2 stream having the mass flow rate Ma1 and Ma2 and also having different moisture content and enthalpy are getting mixed, okay, and most of the time they will end up in a intermediate condition, okay. So, we can calculate the mass by Ma1 plus Ma2, that is equal to Ma3, and all other property if you want to calculate. So, that will be based on this equation, like for the moisture content Ma1 into W1 plus Ma2 W2, that is equal to Ma1 plus Ma2 into W3, because they will have a new or change humidity from the inlet and outlet stream. So, this way we can calculate the other properties, for example enthalpy, okay. So, Ma1, stream Ma1 and stream Ma2, they have a different dry bulb temperature. When they get mixed, we are getting a different dry bulb temperature and all other the different humidity and enthalpy conditions. So, if we take an example for air at 20 degree Celsius, 40% relative humidity is mixed adiabatically with air at 40 degree Celsius, 40% RH in the ratio of 1 kg of former with 2 kg of the latter on the dry basis. find the final condition, that is humidity and enthalpy of the air. Okay. So, what we can do from the psychrometric chart for the condition 1, because we know that 2 condition if it is given, so we can calculate all other conditions. So, 20 degree Celsius and 40% relative humidity, that is stream 1. So, we can calculate what is the humidity of that from the chart. So, we are getting 0.0058 kg H2O per kg dry air, and also we have calculated enthalpy of that. Similarly, condition H2 40 degree Celsius and 40% RH, corresponding to that what is humidity, specific humidity, and what is the enthalpy. So, we will use this equation to solve the humidity of the final stream, and also we will use this equation, that is mass into enthalpy balance. Okay. So, that will give us the value of what will be the enthalpy of the stream, that is after mixing. So, we will stop here, we will continue in the next class. Thank you.